Okay, so everybody, hello. So Matt and I will just present what MASSIF-1 does. Well, I hope that most of you knows already. For the one who's got any question or anything, just we've got the chat open and we keep an eye on it. So either you raise your hand or you put something in the chat or you just open your microphone and you ask. I mean, don't be afraid to stop us. If we can make it interactively, that would be much better for everybody. So don't hesitate. Okay, right. So MASSIF-1 is the automated beamline. You heard about it this morning by Serena already. Because it's an automated beamline, we do remote data collection. Even more than remote data collection, you just send us the crystal, that's it. So before doing that, obviously, you have to tell us when you want to send and when you want to do your experiment. So basically, that's done through the Google Calendar. We have in front of us at the moment. So basically, you've got the month here. And for all the one, you can see that that's people putting their name in. So for example, let's say 2357 here. So they tell us that they want to collect on the 15th of February next week. And they've got an average of 70 sample. Basically, that's the only information we need to book the experiment. The only thing we also need, in fact, is that you invite Debbie in the calendar, which means that every time you write something, you don't have to tell Debbie, but automatically Google will tell her that you book some time, and according to the number of sample you said you will send us, then she will be able to process the experiments, which means that the A form will be published, etc., etc. You will receive the invitation, and all the administrative will start from that point. Okay, so don't forget to invite her. I mean, if you forget, that's not great, but still, we all, Debbie, Matt, and I, we keep an eye on it, and if something appears suddenly when we try to schedule it properly. The number of samples as well, it's not something we want to be very precise. That just tell us how many samples we'll be able to process during the day. So we don't want to be overloaded, because the problem is, like, if we are overloaded, it doesn't mean that your crystal won't be processed, but they will be processed later on, and they will be in the queue, and they will just carry on over the queue. So if the queue is too big, then it's starting to be a bit of a problem for us. So basically, if you tell us a rough number, that's good enough. Okay. Well, don't try to multiplicate your sample by a factor 2 or 3, because that starts to be a problematic. But if you say 70 and you've got 80 or 90, then it doesn't matter very much.
We currently limit it to 160 in 24 hours, which is roughly what we can do. But again, don't feel that that's a strict limit. If you have 180, just put that in. It's just to try and block off the time so we don't overfill it.
And the other thing, which is in the same line, is that your beam time has been allocated for 6 months, and you know how many shifts you have been allocated. So if you go over that, it doesn't matter very much either. We'll process your sample anyway, so that's for sure. And the other thing is, like, the BTAP, the next run, will see that you need more beam time on MASSIF-1 than has been allocated, and your number will be increased accordingly. So, voilà, we are very flexible. We like the fact that we are very flexible, and we try our best to make it flexible as much as we can. Okay, so if you help us in making the flexibility still available for all of you, that's even better.
Just to add to that, in terms of the day that you book, we always do our best to collect on that day, but we try and do it within three working beam days, we call it, of that date. So it can be later or it could be earlier as well. So if your crystals are ready in advance, please feel free to send them, because we can always run them earlier if we have a gap in the schedule or someone else's samples haven't arrived yet. So basically, the sooner we have the samples, the better.
Which also means that will help us a lot as well, is that when you send the crystal, make sure that your shipment has been will come to the shipment, and how you can fill that in I/B. The shipment is properly done as well, because it is for a reason. Don't wait the day the beam time has been allocated to fill up the shipment, because as Matt would just say, if we are in advance, which is very often the case, then we don't like the fact that we have to wait for the shipment to be done and sending email to people saying, could you do the shipment because we want to process your sample. So please try to, as soon as you send the shipment, try to put all the sample in the shipment and ready to be collected. That helps us a lot.
I think that's it for the calendar.
Yeah, for the calendar, that's it, I think, except if there is any questions or anything like that, which is not the case. So how do we process then? Because as soon as you have the beam time which has been allocated and you went through the A form and everything, which is all the safety and administration parts. So basically everything, the only thing you have to do is telling us what you are sending us. Okay, so I put here some shipment which has been already created. Okay, so here you've got all the pucks. Keep in mind, first of all, that as 23.2 and Max was saying this morning, we collect only in unipuck, and that's it. We don't allow SC3. And as far as I can remember, for a long time, it hasn't been the case that we receive the SC3 pucks. So this seems to be in people's mind pretty well, which is great, because that helps us a lot as well. Okay, so voila. So you have to send us unipuck, and basically what you have to do, if you can add a parcel or whatever, but I can edit this one, for example, which is there. And that's the only information we require from you, okay? And the most fundamental one is the two things Serena said already this morning, which is the protein acronym and the sample name. Okay, the protein acronym is already defined because that's come from your A form. Okay, so in the A form, we've got all these samples which have been created and accepted by the safety. So they are all imported in I/B automatically. So that's one thing. So if you've got any other protein acronym, any other subject you want to work with, first of all, you have to have that in the A form in the sample sheet, obviously, which means that it will be accredited, it will be accepted by the safety, etc., etc. And as soon as you do that, automatically it will come up in XC, I/B, sorry, one way or the other. And the other thing we need is the sample name, because based on the protein acronym and the sample name, we base all the directory and how the data are collected and processed. Okay, so that's the two things we need. All the rest, you can leave it blank, it doesn't matter. However, you can always give us more information. So, for example, the pin barcode, if you want to, because that's something we could use if we want. We can go for the crystal form as well, which means that for the moment it's undefined for all of them, but you can define whatever you want, which means that you define the space group, obviously, the cell dimension, and that's all be used later on if you want to fold the space group or stuff like that. Okay, so that's just to help you in keeping a track of which sample you are processing, or which type of sample you are processing under the protein acronym and the sample name.
And importantly as well, this will be used to force that space group doing characterization. So if the space group is defined there, it means that you'll only get the strategy for that space group. So if it has a tendency to change, or if you get it wrong, that means that characterization will fail where it's an incorrect space group. Which isn't a disaster because we'll always collect a default data set, but just to underline that you should be sure that the space group is correct.
Which is also very good because Matthew is presenting the fact that you can mislead to what you will be collecting, but that could be also very, very good. For example, if we always take the same example as the orthorhombic, which is a wrong not an orthorhombic, but monoclinic, then if you force the monoclinic, all the characterization and all the strategy will be calculated with the monoclinic, which could be also a very good thing. Okay, so one way or the other, make sure that what you expect the software to do is doing the right thing. Okay, then we've got the experiment type. Okay, so where you've got all the M-Express, E, F, O, etc., etc., etc. So I won't go through that very much. Apart from, if I look at it, I should have somewhere. It's behind the thing. Voila. Okay, so there is a web page. So if you look for the workflow in MASSIF-1, you've got a web page where it explains everything all this experiment type do. Sorry. Okay. So if you don't do anything, if you don't say anything, sorry. By default, what we do is M-Express E, which is the full Montier, we call it, which means that we are doing all the centering, optical centering, X-ray centering, etc., etc., etc. I'll come to that later on, but that's basically the full Montier, as I say. Okay. Also the size of the beam according to the size of the crystal, tailoring, etc., etc. Okay. All the others, basically, except if we're talking about the SAD, but all the others are kind of something which is a bit of shortcut of some of them. Okay, so which means that some of the steps in the M-Express E are jumped over because we don't want to use it. So some people like that. You can go through this page and you will see that's pretty obvious. What we do. I mean, some of these M-Express are quicker than the others and everything, but that doesn't matter for you because I mean, basically you are charged, let's say, according to the number of sample and not the time we spend on your crystal. Okay.
So we're happy for you to choose the most complex workflows that you like. Doesn't make any difference. We're very happy when you use them. Yeah. Okay.
We can come to that later on another question about any plan for MASSIF-2. Okay, so that's not related to MASSIF-1 for the time being, but we can come back to that.
Good question.
That's a very good question still. That's true. Any resolution, that's an interesting thing you can provide us. It means that basically we do the characterization and more than the characterization, all the mesh, etc., to a 2-angstrom default resolution. Okay, which means that if you don't say anything, we bring we bring the detector at 2-angstrom resolution, and we do the mesh, the X-ray centering, and the characterization to this resolution. Okay, if for a reason or another the crystal diffract more or less, we redo the characterization if needed or not, etc., etc. So obviously, we'll always collect the data set at the best resolution the crystal is diffracting. Still, for doing all this characterization, we go to the resolution of 2-angstrom if we don't say anything. But for example, let's say you've got a crystal diffracting very, very well. That's one option. Then it means that the characterization will be done twice because you will be at the corner of the detector, and obviously we won't be able to do the strategy properly. So we have to bring the detector closer and redo the characterization. On the other hand, which is on the other side of the resolution, means that if your crystal diffract at, let's say, 4-angstrom, then it means that you will just have the center of the detector where we will have the diffraction, which means that the calculation of the dose score for the mesh, for example, and this kind of stuff, won't be great, and the characterization, obviously. So we'll have to move the detector back. Okay, which is a problem as well, because then it means that we have to do the experiment, well, not the experiment, but we have to expose your crystal for 2 characterization, for example, and the calculation of the centering won't be great either. So if you've got a rough idea about the resolution, that helps us in doing the right thing the first time much better. Keep in mind still that your crystal, if we find out that it diffracts more or less than what you expected, we'll always collect it to the best resolution the crystal can do.
There's an extra advantage here as well, because this is the resolution that's set if characterization fails. So if for some reason we can't define what resolution it is, it means if you know very well that your crystals diffract to high resolution. It means that default data sets will always be collected to a high resolution, which is probably better than defaulting to 2, which is the option if you haven't put anything in and we can't characterize. But again, if it diffracts that well, it'll work anyway. But it's always worth having that value in there if you're pretty sure of it. I'd just like to say as well that even so, it's actually only for the mesh scans that it would be placed here. So for characterization, we already do a pre-calculation of resolution. So we would start higher if you say higher, but if you don't put anything, we already move it higher or lower if it's better. So it's already pretty good actually if you don't put a value.
Okay. Required resolution, that's more if you don't want to collect if the resolution is not higher than expected. So that's something, I mean, basically nobody used that very much. Because people just collect and they throw it afterwards instead of doing it before. Okay, beam diameter, that's an interesting one. Also, by default, since the EBS, because before that we were starting with the 50 micron diameter, nowadays after the EBS, now we are 30 microns, which means that once again, all the X-ray centering and the characterization is done at this 30 microns default beam size, okay? Which is great because it's a decent value for the intensity we have, which means that the mesh and the characterization is, let's say, pretty quick. Okay, still, that could be a problem if you've got a very, very small crystal. Okay, because basically with this kind of big beam, then you might not miss the crystal, that's not the point, but not characterize very well all the position of your crystal. That could be also a problem if the crystal is very anisotropic or different quality over the length of the crystal, for example, over the surface of the crystal, because then you want to calculate all this position much more carefully. You want to sample your crystal much more carefully. Okay, so in that respect, then a beam diameter which is less than 30 microns could be a good thing. To do. Keep in mind, and still, and that's more for us than for you again, but still that would be good to know. It's still good to know. Obviously, if you've got a smaller beam, because we are not focusing the beam, but we are putting the aperture in, which means that we are reducing the intensity. So obviously, if you take a smaller beam than the 30 microns, then the mesh and the line scan, which means the X-ray centering, the characterization, takes a bit more time. So that's something which is good to know. But I mean, 30 microns very often, because that's what we measured already. It's roughly all the sample well, not all, but the vast majority of the crystal we have on the beamline. So that's already a good thing to start with.
So bear in mind as well that if you do fix the beam diameter here, it remains fixed for the whole experiment. So if you leave it blank, we will expand or contract the beam appropriately. But if you put 50 microns in, we do the mesh lines characterization and data collection at 50 microns, which might be what you want. But again, it's worth knowing if you do have 10 micron crystals, you fix it to 10 and that's fine. But if you expect a variation in size, it's probably better to stick to the dynamic beam size.
Okay. Number of positions. I think Serin mentioned that also in this morning. Well, that's pretty obvious. That's the number of crystals you've got in your loop. Okay. Voila. So that's it. Once again, I mean, we trust you. So if you say that you've got 10 crystals, then we'll try to find 10 crystals in it. Okay. We are trying to be clever as well, which means that out of the mesh, when we calculate the mesh, we know obviously the size of the beam. So obviously, if two spots or two images are next to each other, basically we consider that as a single crystal. Okay. So saying that means that if you got 10 crystals, we try to find the 10 positions which are not overlapping with the beam size, obviously. And we collect, or we try to collect 10 positions. Okay, so once again, I mean, in terms of time, that's pretty demanding. So just make sure that the number of positions are really number of positions you got in your loop. I mean, don't put 10 because you say, well, I might have some microcrystals here, and I will be able to find something a bit as good as I can find it. Okay, so voila.
That being said, as well, we do any crystals that are below 10% of the best crystal are cut out. So we can't. If you may have 10 crystals in there, but if only 3 of them diffract to a decent resolution, we only collect on 3. I would also just say as well that the number of positions here, if you selected M-Express E, the number of positions you'll collect complete data sets as you move along the different crystals. If you selected M-Express P, which is our pseudo helical, the default number, it will always be 5, so it will collect from 5 positions for the pseudo helical, but you can increase that number or decrease it. So if you only want a helical data collection on 3 positions, you can put 3 here, or if you want it on 10 or 15 positions, you can put that in. Again, bearing in mind that it should be, you should be able to fit that many positions in. So in fact, you could do a nice combination here of M-Express P, setting the beam diameter, for example, to 10 microns, and putting in a very large number of positions if you have a long thin needle.
Okay.
That.
AIM multiplicity, like AIM resolution, is pretty obvious. So it's just depending on the multiplicity you want. If you want bigger than expected, then what we calculate with characterization, we go for that. Once again, I mean, this kind of information like AIM multiplicity, AIM completeness, we trust you 100%. So if you say you want something, we try our best to make it the way you want it. Okay, we don't do anything else. Okay, so that's both of them. So the force space group is just, once again, to force the space group the way you want. Once again, for the characterization, that's exactly the same thing as the crystal form, basically.
But with the distinct difference that it doesn't force the downstream processing. So I don't know why you want to do that, but the option is there if you want to force the space group for characterization to be P1, for example, but you want it to be processed as
P2
in whatever, or if you want the processing to decide, you can do that. So that option exists.
Okay, radiation sensitivity, that's basically for doser calculation when you do the strategy. So we take the doser value, the default value from doser for the sensitivity of the crystal according to what Sasha measured roughly for all the proteins in the data which have been collected here. And then if you think that your crystal is more sensitive or less sensitive, then you can increase this number. Let's say if you've got a sensitive of 2, means that according to the default value, then the crystal is twice more sensitive than expected, etc., etc., etc. So that's something you can play with. If you know that your crystal is more resistant or more sensitive to the beam.
Keep in mind that the strategy calculation already accounts for crystal size and beam size and everything else and flux. So very often, if you've got big crystals, they'll get hit a lot harder than you would expect normally. So you probably don't need to play a huge amount with this factor, but people have shown that for very sort of radiation hard crystals, you can decrease it down to 0.5, and you can increase your I over sig I or what have you if you really want to.
That's basically, I mean, you use that only if you've got a pretty good experience of the beamline and the crystal you're putting in the beamline. So which could be definitely the case if you are doing a lot of same crystals and stuff like that. Okay.
And you could use it actually as well. Some people have used it to do very, very, very low dose data sets. So if you want to go down to the sort of kilogray regime, you can put a radiation sensitivity of about 100 in, and you'll collect very low dose data sets, which might be something you want if you've got a sensitive ligand or what have
you. Okay, Smilestring is pretty obvious as well. You can put the Smilestring if you got any ligand in your protein. So obviously, if you want that to be used, it means that the protein or the protein acronym you define has got a PDB as well, because it means that the Smilestring can be fit in only if a molecular replacement has been done previously. Okay, so obviously you need to give that to us, because that's the molecular replacement is done automatically if the PDB is provided to us. Okay, total rotation angle, pretty obvious as well. So if you don't want to play with the multiplicity or the completeness or whatever, and you want to collect a certain number of degrees, please go ahead and do that. So that's much better than saying the wrong space group or this kind of stuff, because people used to do that. That's one of the reasons we introduced that, in saying that everything was P1. Okay, right. So instead of doing that, we tell you, or tell us how much you want to collect, and whatever the characterization says, and the total angle we should collect according to the characterization, will collect the number of degrees you ask us to do, but with the characterization parameters, except the total angle. And the minimum oscillation angle is the same thing. So basically that's done through the characterization. If you want to have like a default value of something, just tell us, and that's something we'll do.
It's not a default, unfortunately. It's a minimum.
It's a minimum. Yes, sorry. Yes.
Yeah. So it means that you won't go below that value, but you could go above it.
Above it. Yes. True. Anything else? Question?
We have a couple of questions.
Yes.
So Juliet asks, the number of positions can be either many positions collected on the same crystal or many small crystals in the same loop. That is correct. And depending on whether you've selected M-Express E or M-Express P, if it's E, you'll have a full data collection from each point, be it a separate crystal or a separate position. Whereas at M-Express P, you will have a sub-wedge collected to eventually make a full data set from each position. If that's clear. And then Sanchari asks, what about photo reduction of metal sensors? I presume you mean for the dose. I don't know, but yeah, you can control the dose to try and reduce photo reduction of metal sensors. Is that what you meant?
For the radiation sensitivity, if we have metal centers, how do we mention it then?
Again, you say put that in this radiation sensitivity.
Yes.
So you push this up to a very high value. Probably if you've got something very specific like that, you probably better to contact us beforehand, because we could do a specific workflow that limits the. We've done this for people before that has a very specific dose limit if you need it.
Okay.
Yeah, if you tell us how much you want to, what's the dose you want to for your full data set, that's something we can provide to the software. And automatically the characterization will be done accordingly to the number of photons you want to deposit on your crystal. Okay, so if it's like a value you want, that's something we can definitely do easily.
We don't do it as it's a very unusual request, so we don't put it into ICE/B, but it's something we can easily do for you, especially if you like. And I should underline that actually, that if you have any sort of unusual requirements, it's actually relatively easy for us to accommodate you. If you want with a specialized workflow that has some sort of requirement that isn't in the usual ones that we've just described. Yep.
Okay, so that's it, I think, for the information we need from you guys. Basically, if you give us that, well, that's it. Your data will be collected.
And I would say that if you're unsure for any of these things, I would just leave it blank mostly, because the system does a really very, very good job. So if you have a new crystal system, or you're not sure what resolution you should set or whatever, I would just leave the whole thing blank, and the system does a really excellent job of working out what it should do.
Okay. So we can go, voila. So as soon as this is done and we start the experiment, first of all, before saying anything, automatically, as soon as we start the your time, you receive an email, and as soon as, if it's defined in the sample sheet, as soon as we start your protein, and you are not the bag responsible, you also receive an email saying we start your sample automatically. Okay, So you know when this is started and what time we are doing the job. Okay. So what do we do on the beamline as soon as well, what the beamline does, in fact, because we don't do anything, everything is done automatically. Obviously, because if user don't come, it doesn't mean that we are here to do it, but all the machine is doing that for us, which also means 6 days a day, a week, and 24 hours a day. Okay, so basically what we do, first of all, we load the sample. So the flex, because we got a flex since the EBS, we got the flex sample changer, like all the other beamlines. So the sample changer mount the sample on the gradiometer. And as soon as this is done, then we center it optically. First of all, so there is 3 runs of optical centering. And as soon as the loop is centered, because that's a loop centering, nothing else. As soon as the loop is centered, we rotate it 360 degrees and we take 12 images 30 degrees apart. Okay. That allows us to have like an idea about the loop shape and obviously the what's inside optically. Okay, that allows us to calculate the box where we want to do the mesh. Okay, so the red box is where we think the loop is and where the mesh will be done. What I'm calling the mesh is in fact the scanning of this red box by line using the diffractometer and the diffraction, and then allow us to center the crystal. So as soon as the data collection is done, the mesh scan is done, we obtain a heat map. That would be easier. Heat map. Okay, you can see here. So the heat map here. So based on the dose score, obviously. And that's what we have here. Basically, show us where is the best part of the crystal, and if it's different crystal and everything. Okay. So as soon as this is done, we are able to center in 2 dimensions already the crystal, obviously, which means that what we call the horizontal, which is the phi y, doesn't matter, and vertically, and then we rotate 90 degrees, and that's what Matt is showing at the moment, and we scan vertically the crystal again, and according to those, we are able to center the crystal. So as soon as we are centered at 0 and 90 degrees, obviously, the crystal must be aligned. As soon as this is aligned, then we do the characterization. Okay, and we calculate the best strategy. Okay, and there are 2 things here we can show you. Is that first of all, if the resolution, because that has been set up at 2 angstrom resolution as a default, but obviously the crystal is diffracting much better than that. So, and obviously, if you just have the corner of the detector telling you how much your crystal is diffracting, that's very difficult to estimate the resolution. So instead of doing that and doing a wrong estimation, then basically we bring up the detector closer, okay, and we recalculate a characterization according to the real value of the resolution, which means that here there are 2 runs of a characterization. Can be avoided easily if the user will have tell us, or the user will have known, because sometimes you don't, okay. But if they will have known that the crystal is diffracting much better, then we'll have set up the resolution to, let's say, 1.5 or something like that, and then we'll have saved 1 characterization, which means 4 images. Okay, so that's one thing. And the other thing, which is very interesting in this this sample, sorry, is that is a P1, and that's something Serena mentioned also this morning. Is like, because it's a low symmetry, obviously there is a blind region, whatever the crystal is mounted. So which means that as soon as the first data set has been collected, we open the kappa to 40 degrees, 45, I can remember 40
degrees.
degrees.
Yeah.
So we open the kappa to 40 degrees. So obviously, because the kappa is not perfect, mechanically speaking, it means that we have to realign the crystal. So we redo a mesh centering on a very much smaller rectangle, obviously. And we rotate 90 degrees, which means that we align at 90 degrees. So as soon as this is done with the open kappa, we can, the crystal is properly aligned. And obviously, once this is done, we can recollect these new data sets with the open kappa. Matt, you're jumping everywhere.
Sorry, I just want to show. I want to show the results of that that data collection, so you can see what it looks like. So just to stress that you don't actually have to. You don't have to say that you want a kappa strategy. We do this automatically. So as soon as a low symmetry space group that diffracts better than 2 angstroms is detected, you'll see this message here at the bottom in EXE saying that we've detected a P1 better than 2 angstroms. So there are 2, and you can in fact see here that the movement of the crystal, the rotation of the kappa, and what you'll get. I'm afraid we don't do all the work for you yet. You still have to get these two separate data sets that are processed separately, and the best idea is to be able to merge them afterwards, and you should remove most of the missing wedges of data that you'll have with this low symmetry space group. So we're working with global phasing, and we hope to sort of do more complex. So this is a bit it's better than nothing, but it's not a very intelligent way to do it, just opening kappa randomly, not randomly, but to a fixed orientation. So towards the middle of this year, we hope to have the global phasing workflows in place, where we have either a SAD strategy or low symmetry strategies that will be multiple wedge, and they should be automatically merged together and presented to you as a single, very complete data set. And again, you won't have to request this. It will just be done automatically, and you'll just get, hopefully, the best possible data from each sample, whether it's low symmetry or SAD or what have you.
And the good thing is that's another extra thing we'll get out of that, is that by using the global phasing processing, we'll be able to have a better idea about the anisotropy of your crystal and stuff like that, which will be another good thing to know about. Okay. What else do we got a couple of questions.
Okay. So we have a question. Could you please explain again how you interpret the heat map results? Okay.
Yeah. Okay, right. We can come back to that. That's not difficult.
So we could do that one.
Well, okay. So in fact, we got 2 heat maps. The first one is just, well, the rough heat map from Dozer, and not Dozer M, if we got it at the no, we don't have it right. You have to go for the other one. This one, yes. Okay, right. So basically you've got a scale on the right of it. Okay, that's the Dozer score. So the higher the score is, the higher the quality of your crystal is. Okay, so basically, and we do something a bit clever as well here, is that it means that because we know the biggest size of the beam we can have and everything, we look around the best diffracting image, okay, according to Dozer, and we look around if the images are with the same quality, which means that it's the same crystal with the same quality, which means that we can increase and tailor the beam size according to the beam, the crystal size. Okay, this is the other map we can obtain not from Dozer, but Dozer M. Okay, which is in fact the same program or whatever. This one's got a bit more option, a bit more information you can get out of it. It's like we look on all this diffraction image, and we try to see if it's the same crystal or not. And in fact, here we can say that it's a bit biased because, I mean, we are pretty sure that it's all the same crystal, but according to those, he says that there are more than one diffraction pattern. Okay, so number one, you can see in the middle, is the best crystal, and there are 4 images with the same quality and the same diffraction pattern, and all around there are other diffraction patterns which are not related to the number one. Okay, but it's just because those are for the moment, it's something we installed not a long time ago, and Sasha is still working trying to make it a bit more efficient, and that's also what that was presented on MASSIF-3, where they are trying to do a 2D meshes. Instead of doing a line scan for the second scan, they try to do a mesh scan again, try to make sure that after rotation, you've got the same crystal all over the place. So that's something we are still trying to improve, which is not working as the best at the moment, but we are working on.
What's nice is that it defines the beam size at this point, and it also eliminates areas that have overlap reflections. So one thing that DOSA didn't do was couldn't really distinguish between regions where you had overlap, multiple crystals or single crystals, whereas now we select the best part that has a single crystal that's homogeneous and adapt the beam size at that point as well. So I mean, I think we should crunch the numbers, but I think we're getting better data from using DOSA M than from just straight DOSA. I hope that answers your question.
Yes, thank you very much.
And there was another question.
No, I think that's it actually. Yeah, that's Courtney saying she's
okay, right. Okay. What else? Well, then it's the processing, I guess. Jesus. Voila. No, the one just before. Okay, right. So obviously, as soon as your data have been collected, we start processing it, which means that processing is not only processing without doing anything. So we got several different packages running in parallel, and we try to print out the best one at the end of the processing, and then it tells you a couple of information you need to know. And you can obviously download either the log or the results or whatever you need to. Okay. That's one thing, but also if you provide, so by default, we run a SAD processing as well. So which means that we're checking out if there is any anomalous signal. That's without saying anything, because we are just above the selenium edge. So if there is any anomalous signal and we are able to spot it in the data, we run a SAD processing and we try to solve the structure of any issue like that. That's one thing. And if it's the case and we are able to solve it, then automatically we receive an email saying that has been solved with an image, and you receive an email about that. That's one thing. The other thing is, like, if you provided us with the PDB, then obviously we are able to run the molecular replacement, and if there is anything in the in your sample, if you provide a Smilestring or whatever, we try to fit the ligands inside the map as well. Okay, and basically that's the only thing I want to say.
I think that's it from start to finish,
yes,
isn't it?
Yes. Yeah. Okay. Just to emphasize once again what Matt just said before, that's what we do, okay? And we try our best to make it working as much as we can. So if there is anything you feel missing or you want to be done differently or whatever, and it's not implemented already, please tell us, because I mean, all this software, and especially the workflow, which means that the program which is running all the different steps of the strategy or the characterization, data collection, etc., that's all done by mainly Olaf here, which means that we got hands-on it and we can modify it as much as we can. Okay, so if there is anything you want to be done differently, like for example the radiation or the number of photons you want to deposit, all this kind of stuff, let us know. Obviously, you have to tell us a bit in advance because that's not something we will be able to change in 5 minutes, especially if it's a bit tricky. But we are definitely more than happy to do it and fit exactly what you want to have and the way you want the experiment to be done. Pedro, you can
ask away.
Hi, Didier.
Hi.
So you said the thing about the aimed resolution that you start at 2 angstrom, and if the crystal diffracts much more than that, you waste the characterization. But how tolerant is the system? For example, if I set the aimed resolution to 1.5 and the crystal diffracts to 1.3, is it enough? Can it just recalculate the strategy based on that and move the detector without having to run a second characterization?
Yes, definitely. Yes, definitely. It's just about the number of spots you've got in the corner, basically. Okay, so between 1.5 and 1.3, I mean, 80% of the spots are all there, so it doesn't matter very much. So, but that's more if you got well, exactly the example we show is like the detector was at 2 angstrom and we got 1.3 or even better. You see, I mean, 0.1, 0.2 difference is nothing, or even 0.3 is nothing. I would say up to 0.5 is all right, okay? But below that, then when you start to have like between 2 and less than 1.5, it's starting to be a bit tricky for the strategy to be calculated properly. So basically, that's it. So if we are talking of plus or minus 0.2, it doesn't matter.
Another thing is that I have noticed in some of my crystals that the strategy gives me, for example, a 1.4 resolution. They usually diffract very well, but then the processing goes down to 1.2 or so. And so I end up with an incomplete data set to 1.2 because the detector was set to 1.4. Do you have that experience as well in some cases, or is it just me?
No, the problem is that the strategy is calculated on I over sig I, and the processing is done on CC half these days. So you will always have a slight décalage on, I can't speak English anymore, a slight difference between the two. In that the problem, there's no, so the processing will always push it further than the prediction to some extent. But what I would say then is that you could play with, I think if you played with your fudge factor for the radiation tolerance might make a big difference. Because if you have slightly higher tolerance on radiation, you can squeeze a bit more resolution out. Best will push that a bit further.
Okay, would you say like 0.9, 0.8 instead of 1?
0.5 I would push it to. If it's quite robust, then that should be all right. But okay. Again, if you have a feeling like this, Pedro, we can try it on 3 or 4 samples and see if it makes a difference, and then put it back again or what have you in discussion with you.
No, the weird stuff is that sometimes the strategy is actually correct, that I get the resolution it predicted, but then some other times it's underestimated. So it's really difficult to know beforehand, because nowadays these detectors are very sensitive. They have virtually no noise, so the images are much cleaner.
Agreed. What we see is that there's an extremely good correlation over all of the samples we've ever processed between predicted and achieved resolution, but it's very slightly below. So Edna does very slightly tend to underestimate the final resolution that you can get, but it can't be perfect all the time either.
Okay, thank you.
Are there any more questions?
If not, then we'll just say again what we are doing at the moment, which is more development, but shortly will become available to all of you guys, which is the dehydration and the harvester and all this kind of stuff. But Matt will present that, and that's basically just a more practical view of what Serena showed already, and that's why we are working mainly on that.
Just to come back to Pedro's point, I found the chart to show the correlation between the ranking resolution, which is the resolution predicted by for the strategy, and they actually achieved resolution from auto-processing. And you can see that red line is perfect match between the two, and you can see that it's pretty good actually. So it tends to go down at low resolutions because obviously it's based on B factor. So that, you know, below kind of 4 or 5, you get a very poor B factor, so it's difficult to predict the resolution. But I mean, I think it does a pretty good job. We try and make it better all the time, but there we go. Okay. Right. So yeah, Serena said this morning, we're currently changing the beamline quite significantly. I can find my my slide. Isn't very good, but anyway, I wanted to talk a little bit about what we can do with the what we can do with the harvester now that we've got it mounted. So from Serena's presentation this morning, you'd have seen that we can carry on doing cryo experiments, but we now have the crystal direct harvester, and this means that we can automatically harvest crystals from crystal direct plates, pick them up with the robot, and put them straight onto the goniometer. And so, what are the advantages here? And obviously, we can do cryo experiments in a faster fashion, and we can do all sorts of weird ligand soaking and cryo experiments and time courses and things like that. But I think one of the things that we really want to offer is to bring fully automated data collection out of the cryo regime and bring it into the room temperature regime. Because something that we've been working on for a long time is both data collection at ambient temperatures, but also dehydration experiments. And these are actually very tedious and laborious experiments to do by hand, as I'm sure you all know, either mounting crystals in sleeves and then putting them onto the goniometer is very painful to do, and also restricts the kind of number of experiments you can do because you have a long sort of capillary-like thing on the end. And then dehydration experiments as well, it's quite a pain to mount the crystals, and then you have to sit there for hours while it dehydrates and you expose and see if there's any sort of change induced on your crystal system from dehydration. So what we can do with the harvester is fully automate these experiments. So what it means is that you won't have to come, you won't have to do them. You just have to either send your protein to HTX or send us crystal direct plates. We can then put these plates into the harvester and then run through them and mount them, either doing large-scale room temperature data collections or do large-scale, well, slightly less large-scale, but high-throughput automated dehydration experiments. So we have a nice interface in MX-Cube, which brings up the crystals that need to be harvested. As Serena was showing this morning, we can just add a workflow to each of these samples as they're harvested. So this can either just be for normal data collection. We've also developed a new workflow for room temperature data collection, where we do a very low dose mesh and line scan followed by a fixed dose data collection, and we've had some very encouraging results with that. We sort of keep the dose to around 100 kilogram. We get reasonable data actually from good systems, and we can play around with that to have workflows that can piece together multiple wedges and things like that. Yeah, and then everything else runs as it does before, so it's actually very similar. So just to show you, I don't want to go over the process, but you probably know that you've got the drops get aspirated, so the liquid is taken away and they're then mounted, laser photo ablated onto these mounts. This is terrible slides. We then mount them on the beamline. Because we have the kappa, we can orient them in the same direction as they're mounted, so we know exactly where the crystal is. It's not showing that all the things are corrupted, but we can move directly to the crystal so that we can then very quickly do a small mesh scan and do room temperature data collection, or we can start a workflow for dehydration. So the great thing is that we can either have the cryostream in position here, or we can move the humidity control device in. So we can either then match the relative humidity of the stream to the relative humidity that matches your crystal, and I'll come on to that in 1 second. It's a very easy calculation. Or you can start dehydrate for room temperature, or you can start dehydration experiments. So just to very quickly show what we do, this is an example we worked on a while ago with a human blood transport protein called afamine. I mean, there are numerous examples in the literature. And dehydration has several effects. Sort of the one everyone's always after is trying to increase resolution, but it also does a lot of things like reduce anisotropy, increases overall order. You can get changes in ligand binding by changing dehydration. There are all sorts of things that can go well. So what happened here was actually these crystals diffracted. Some of them diffracted very, very well, but it was very, very few, and we couldn't really tell why. And what we found was that we could actually dehydrate these crystals, and you started around 100%, which is the relative humidity and equilibrium with the mother liquor. And you keep dehydrating and dehydrating, and you don't get much change in either the doser score or the number of spots. But at about 87% relative humidity, you get this really significant phase change, where you get a huge, increase of diffraction from about 3 to around 2 angstroms, and also quite a significant change in the unit cell volume. And at the same time, you could see a big decrease in mosaic spread and a decrease in the A edge of the unit cell. And this actually made a huge difference to the project. And what was nice is that you can combine, now that we've got MASSIF-1, we can combine these sort of dehydration experiments with an automatically mounted crystal with the sort of things that we've just been talking about, where we can then collect from multiple positions afterwards and do calculations to see what protocol gives us the best resolution, and then apply that to crystals and cryocool them and remount them. So we're pretty excited about the possibilities for full automation. And just to show you the sort of effect it had, so this is just comparing the 2 unit cells. We got a phase change from a monoclinic unit cell to an orthorhombic, and you get massive stabilization of many of the side loops that you can't see. You can see here, this is just a representation of where the movement is between dehydrated and undehydrated. You can see that the whole thing gets stabilized a lot compared to the undehydrated form. And what was very interesting is we could actually see a ligand bound in the high resolution structure that we couldn't see in the low resolution structure. This is really informing the biology. So again, if anybody has examples of you want to do large scale room temperature data collections, or you want to try out dehydration in an automated fashion, where we're at the stage that we can do these experiments now. So we'd be very happy to do this in an initial stage before we offer it sort of more widely for people to book. And this is just, excuse me, this is just an example of the room temperature data collections. And you can see where with very, very low doses, around about 100 kilogray per crystal, we're getting sort of 2.5 angstrom data from a test system, which we're quite pleased with. Yeah, and then as Serena was saying earlier on, we're going to make this fully automated so we can load a large number of plates, move these between, and we can just keep going with either room temperature or dehydration experiments. And you can just sit back and watch the data come in.
I mean, keep in mind that even if we call it an automated beamline, I mean, there are people and there are projects coming in. So, I mean, if you've got anything you want to do differently or whatever, just tell us. And that's exactly the same for the dehydration or the room temperature or all this kind of project. I mean, we've got all the hardware and the manpower to be able to do it. So, I mean, just come to us and talk to either Matt or myself, and we will be able to find a way of dealing with the experiment we want to do.
So yeah, Mark asks if there's any plans for MASSIF-2. I think you probably have to direct that to Gordon. We're certainly seeing a huge demand on MASSIF-1. I think it would be good to widen the MASSIF-1 model to more beamlines, but it's not up to us.
And as you can see, I mean, this question has been raised already on for 23 and 30B. I mean, that's the plan we have to do. We have to go for as well, and that's something we are still working on, is trying to have this kind of way of working, which is completely automated, even if it's instead of us starting the workflows on all the samples, it could be you guys, the user, starting. But I mean, the automated data collection should be available on all the other beamlines. So if there is nothing more to say, then we can close.
Yep.
Except if we don't see any of other
showing, but yeah, like we say, feel free to get in contact with us if you need any information, and we're always happy to run your samples and